everybody, welcome. Thanks so much for coming to the presentation. If you guys have ever been to the previous ones, I know I recognize a lot of the faces. You guys will know that the presentations we do are presentations that are math related, that you don't need to know math in order to involve yourself with. So it's very, very kind of a cool idea, something that we're very proud of, that we're working hard with. And my presentation, I'm actually going to be the first student to be giving presentations. The other two have been faculty. And I became sort of inspired to give this presentation based on my job. Some of you guys, a lot of you guys actually probably know that I'm a tutor over in the Math Center, which by the way is a great place if you ever do need help coming over and visit us, for sure. But when I was listening to another presentation by a math teacher, his name was Dan Leiter, he opened up his presentation in a way that was almost identical to how I had been feeling, so I'm actually just going to read exactly what he said for his opening because it fits really well. And he started off with saying, imagine a time when you guys had something you loved. So think of a time, a book, a novel, a play, an album, some type of song, and you recommended it to a friend wholeheartedly. And you waited for their reaction, you expected their reaction, and they threw it back in your face and hated it. And just like him, I actually have the exact same experience every single day that I work as a math tutor. Because I work with people who are already exceptionally frustrated with math, and trying to teach them to love it is very, very difficult when they already have such a resentment built up. It seems like it's almost ingrained in our culture nowadays that it's not all right for people to have difficulty with English. If you say that you can't format a sentence, people look at you kind of funny. But if you say that you can't format a fraction, you're also sort of giving an excuse because that's math. And I found this not meshing. It didn't seem to fit in with that, seeing as math is just as important, and I decided to make the presentation based on that. So, reading over here, this is actually a pretty good quote that I think comes up with generally what I feel math is. And with a pencil, I can hold the power to do math, hold the power to make money, hold the power to create art, persuade countries, earn respect of millions of people. This is my weapon of choice, and with it I can create and destroy indefinitely. So, by way of introduction, this is what I believe math is. And in order to show what I think math is and how it's come to be, I'm going to try to run through practically all of the history of math. So we have, what, T-minus 52 minutes and 35,000 years to cover. So bear with me. If you guys don't understand everything that is said, that's all right. I can't say I do either. There's a lot of things in math that are not very easy to get. But follow along. Hopefully you'll pull out some nice things and you'll learn to appreciate math just as much as I do. So first two questions that I'm going to work on in this presentation are, why is it here? So why does math even exist? And second, why is it that any of us should even care? And I'm going to bring up a story from another mathematician. He's a guy from a little bit further on in history. His name is Carl Friedrich Gauss. And it's a story from when he was a child. And the story goes that Carl was sitting in his classroom, and his teacher apparently was getting quite annoyed at his class for being quite rambunctious. And in order to keep them occupied and give them a little bit of rest, he asked every single person in the classroom to sit down and to quietly add up the numbers between 1 and 100. So all the students sit down, they start adding up the numbers between 1 and 100, except for Carl. And Carl instead stares at the page for about 30 seconds, and then writes down the number 5,050. And goes up to the teacher, hands the teacher the number. The teacher, surprised that he could even calculate that fast, believed that he just threw down a random number and didn't actually do the math, and asked him to sit down quietly at his desk until everybody else finished. And when everyone else finished doing it the old-fashioned way, they found the numbers did match. And that's pretty much what math is. Let me go ahead and show you exactly the way that he did that. And it's not a very difficult procedure, but it's kind of hidden. Think about the numbers between 1 and 100, right? 1, 2, 3, 50, 97, 98, 99, and 100. And the way he looked at this was not just simply the numbers adding, right? Typically, if I asked you to add up the numbers between 1 and 100, you do 1 plus 2 plus 3 and continue on that way. He started to find patterns. 1 and 99, 2 and 98, 3 and 97, all of these added up to 100. And if you count up the number of groups of 100 you can create, there are 49 groups. The numbers 1 through 49 have corresponding pairs as higher numbers that you can add in. The only difference, and then you have the last number, the 100 itself, creating 50 groups of 100. So the 50 groups of 100 got to 5,000. The 50 in the middle, which doesn't have anything to match with, gets a 5,050. And that's all math is. Math is finding patterns. It's finding patterns in ways that might not quite be obvious, but that make life a lot easier than doing stuff in the typical conventional way. So, going back to Egypt, ancient math can actually be recorded to about 37,000 years ago, depending on what you call math to be. If you count tick marks that cavemen would put on walls to be counting the seasons to be math, then math goes back further than that. But Egypt is where it started to actually finalize. They began to come up with some rules and some techniques. 5000 BC is about the time this started up, and we see that math was used mostly to handle real-world problems. It was used as a way to figure out taxes, figure out volumes that people were producing so that it was easy to charge people on it. And in addition to this, it was also used very much for areas. If anyone was taking a world history class, Egypt was a very fertile piece of land. The Nile would continuously flood and then retract, putting nutrients into the soil, so it made farming very easy. But the difficulty with that is if you have land and it continuously gets flooded, and you don't have distinguishable boundary marks for your property, the use for finding area became quite inevitable. So they began to find out, how is it that I can report area, length times width for squares. Same thing with rectangles. Triangles were a little bit different, just like you would learn in your geometry class or Algebra 102, 108 class that they offer here. Let's see. And the way that they reported all this was using a hieroglyph system. So the numbers 1 through 9 would be recorded just with simple tick marks. Number 10 upside down U, and then the other increments of 10 up from that, based on different symbols. So you get a frog for 100,000, for example, the god for 1 million. And although this worked very well as opposed to the caveman style of just simply putting tick marks everywhere, when the cavemen went starting to get up to the hundreds or thousands of tick marks, it was not as easy to glance and figure out what that number is. So this system became much more efficient. The difficulty arose when they started doing algebra with it. So whereas we could get the number 1 million, say subtract 1, and they would write it the same way, their symbol for 1 million being the god minus 1 tick mark. And whereas we would just simply put 999,999, they had to do it a little different. They had to say that there were 9 groups of 9 for the symbol 1, 9 groups for 10, 100,000, 10,000, and 100,000. So the simple math operation we would do, 1 million minus 1, took them from writing one symbol to writing multiple, 54. So that was the place where it fell back. So the uses of algebra became difficult. In order to compensate for this, they actually came up with different styles to do their math. And there you go, there's the math that I just showed. And they used multiplication. So multiplication was something new, but they had to do it a little bit different because they did not have the techniques we do now. They didn't have the same, 1 times 5 memorization, simple grouping idea that we have. So they actually came up with a much more clever way. And the way they did was let's say they have 2 different pairs of numbers. I'm going to choose the numbers 3 and 5, just keep it small. So there's my 2 numbers, 3 and 5. They would choose one of them, choose the number 3. And then they take. In one side of the table, they would put 3 objects. In the other side, they would always put 1. Regardless of what the other number was, they would always put 1 in the column. And then all they do would be to continuously double. So the 1 would turn into 2, 2 to 4, this would turn into 6, and the 6 to 12. And then all they did was group. If they wanted to do 3 times 5, they would take the numbers over here, the 1, and find a group that made 5. Here you can take the 4 from the bottom row and the 1 from the top row. And then they would just add together the corresponding groups. They take the 3 from above and the 12 from below, and they find out the 15. And that would be their 3 times 5. So they had very clever ways. But the difference between how Egyptians work math and how we work math is they didn't care why. Why wasn't a prominent feature yet. It worked. They were more of a primitive society. They needed to find an answer. The moment they found a technique in order to create the answer, they mostly dropped at that point. Some people got curious and began to investigate, but overall as a society, the why for math had not been created yet. Also, real quick, another couple things that they did was working with shapes. Once again, that area. And the most difficult shape you could think to find a area for would be a circle. Length times width for a square. Rectangles is very easy. Triangles you can create by cutting squares in half. But circles are more difficult. And the one theory that I found that seems to fit their idea really well actually comes off the game Mancala. It doesn't take too much thought to imagine people playing this game Mancala and realizing that certain numbers fit into the circles very well. So for example here, right, this number of stones here fit very easily into the circular shape. Number 2, not so much. And as you experiment with different numbers that better fit into the circle, you come up with something like this. And so this over here, this is a hexagon. The number of circles going across is the number 9. Now, if you count up the total number of stones there, the total number of stones is 64. And that's just how much it takes to create a hexagon that's that long across. If you take the number 64 and just start rearranging the stones, you get a very nice square. A square with one length being 8 and the other length being 8 as well. So the area of this hexagon helped to create the relationship, go back, that you could have the area within a square was almost exactly equal to the area of the square whose length and width were 8/9 the diameter of the original circle. So working with different creations and moving things around, old-fashioned uses for math, these was how they had to come across it. There were not laws. They had not been established yet. So we're going to give you just a break and actually move to another very early developing area, and that's the Babylonian. And it was in Babylonia that they started to come up with some different ideas, this idea of equals. This hadn't been invented yet, which is kind of strange for us to imagine with our nowadays math presentation, but there was no equals. Equals didn't exist. It's sort of just like if you did scratch work off on a napkin at your Denny's restaurant, you would just come up with an answer. There was no equals. It was just simply what you would create. But they began to work with equations. In addition to that, they also have found artifacts, like the one on the left here, which almost exactly replicated the kind of problems we would see in a classroom setting nowadays. Right? If I have a square whose length is 16, and I create 4 circles inside of it, what is the area encompassed by these circles? And so pretty much math problems for the sake of just simply doing math problems. And these were how they would train their scribes, because scribes were the few people within this civilization that knew how to create math and knew how to use it properly. In the video that I removed this from, they turn this over and there's actually markings on the back by the teacher that are grading. So it is exactly a homework problem that they had the student bring home in order to finish. And the other difference between them and us is they used what's called a base 60 system. And we have a base 10 system of counting, right? We have 9 different symbols, 0 through 9. And then once we run out, we loop upon itself again. We go to 1, 0, and then as we go all the way up to 99, we get 1, 0, 0, and we continue up to 1,000, 10,000. They used a base 60 system. We use base 10 because of our fingers, they counted on their knuckles. So imagine, if you will, right? 3 knuckles on each hand that you can count with your thumb. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You'll come up with 12 different knuckles on this, you hold up your finger on the other hand. So eventually you get 5 groups of 12 getting them their base 60 system. And actually that had a lot of advantages, because our base 10 system is kind of limited. You can really only divide it by 2, 5, and the number in itself. But the base 60 system could be, divided by 1, 2, 3, 4, 5, 6, 10, 12, 15, and all the pairs that went along with it. If I missed a couple, I'm sure you guys can find them. But it was a much more manipulative system, so as far as algebra went, it was a lot easier for them to work with grouping in the pairs that they're used to here. Okay, so base 60 system, they also work with angles. Angles using to measure or charter the different displacement of the stars throughout the sky. Because using distances was not very accurate, because 1, they're incredibly small, and 2, they kept changing. So using angles was a very convenient method. That's why our angles nowadays, there's 360 degrees within a full circular rotation. It's based on the base 60 system they had there. Same thing with our clocks nowadays, why there's 60 minutes and 60 minutes, 60 seconds. They would work with problems where they had a couple more unknowns that helped them out with their areas, but that wasn't quite as present in Egypt.